Great. Then our next speaker, as I said, is Julian Külshammer from Uppsala University, who will speak about the monomorphism category and representations in the stable category.
Yeah, thank you, and thank you for organizing this conference. And yeah, I would like to report on joint work with Nan Gao from Shanghai and Sondre Kvamme from Trondheim and Chrysostomos Psaroudakis from Thessaloniki. Yes, and let me start quite soon. So with some classical results, like Gabriel's finiteness theorem, that I don't have to spend much time on because probably everyone knows it. So let me fix throughout the talk a finite connected acyclic quiver. For many results, you can drop finite and connected. So let me not go into that. And let me introduce RepQC, just a category of representations in the category C. So just covariant functors from the path category of Q to C. Okay, and then in this notation, Gabriel's theorem states that if you have a field K, then the category of representations in vector spaces of this quiver is a finite representation type, if and only if the quiver is of Dynkin type A, D, or E. And of course, you don't need the field to be commutative. It kind of could be a skew field, if you like, to work in this generality instead. Okay, but now you could ask somehow what happens if you generalize this vector spaces to other categories or even to other finite dimensional algebras. And maybe the simplest example of a non-field somehow is maybe a radical square zero Nakayama algebra. So let's take a radical square zero Nakayama algebra. Let's assume it's non-semi-simple. So for example, the dual numbers, and ask when is representations of a quiver in the dual numbers for finite type. And this has been answered. You can find several references in the literature. Shinsky and Skowronski have worked on some general question of when a tensor product of two algebras is a finite representation type. So from their work, you can derive this, that if lambda is hereditary, so it's some product of path algebras of A1 and A2, then the representations in that algebra is a finite representation type, if and only if Q is of type AN for n smaller or equal than 4. And if it's not hereditary, for example, the dual numbers, then if and only if Q is of type AN for n smaller or equal than 3. So that's a quite restrictive list of algebras, and somehow it doesn't have the same flavor of Gabriel's finiteness theorem. Okay. So one natural question in different flavors people have asked somehow, if you can't answer the question of representation type for the whole module category, you could ask for subcategories. That's appeared in many different versions. And the version I want to talk about today is monomorphism categories. So what's the monomorphism category in the setup I'm talking about now? So I go away from Nakayama algebras and go to arbitrary, let's say, Artin algebras. And the representation is called monomorphic if for all vertices, if you take the direct sum of all the arrows going into that vertex, that becomes a monomorphism. So you want the maps on the arrows to be monomorphisms, but not only that, you also want their intersection to be 0, the intersection of the images of the maps in that vertex. So some authors call this the separated monomorphism category because of this property. But I just want to call it the monomorphism category for simplicity. Okay, so now one can ask somehow, when does this subcategory have the property that every object, there are only finitely many indecomposable objects up to isomorphism. Okay, why this subcategory? So let me give several motivations of why I'm interested in this subcategory. First of all, it's a classic problem that people have studied starting from the start of the 20th century. So there's some work by Miller and Hilton, and Birkhoff has worked on it in some pre-quiver flavor, but somehow like that. And therefore, Ringel-Schmidtmeyer, when they study this problem in the case where Q is A2, they call it the Birkhoff problem. And they have some work of generalizing it to arbitrary lambda, but still for Q equals to A2. And then Pu Zhang and his co-authors have worked on the question for general Q and also some variants of it that I don't want to go into. Quite recently, it has also risen in topological data analysis, where you have some sort of grid and with coming from two parameters coming from your data cloud. So Bauer, Bodnan, Oppermann, and Steen have worked on this and published something in 2020 on when this category, in the case that lambda is some sort of path algebra of AN and Q is some AN quiver, when this is a finite type. For me, this is of interest because one interesting class of exact categories is that of exact length categories satisfying a Jordan-Hölder property that's very close to finite dimensional algebras. And this arises in work of Enomoto. And in fact, one can characterize the category of monomorphic representations as the category of modules filtered by these induced simple modules. Okay. And then what was our original motivation is maybe that it's somehow, this category has a natural generalization to a species category that arises in work of Geisler-Schröern and cluster theory and categorification. Okay, so what's our take on it? So let me first mention this Gabriel-type theorem for Nakayama algebras. So if you have a non-semi-simple radical square zero Nakayama algebras, then you have this theorem that the mono category is of finite representation type if and only if Q is of Dünken type A, D, or E. Okay, and then the second part of Gabriel's theorem is also always very important. It's somehow when, how many indecomposables are there? And we can also answer this question. Some explicit formula involving the number of simple lambda modules and the number of non-projective simple lambda modules. Okay, so how does this number arise and from which more general theorem does this theorem follow? And we talk about how we prove it, actually. So first of all, this number here is a sum of two numbers, right? M times the cardinality of Q0 and T times the cardinality of phi plus. So I have to explain both of these summands separately. And the sum is somehow the number of injective modules and the number, or injective objects and the number of non-injective objects. So now I'm switching back to arbitrary Artin algebras. Then mono Q of lambda is always a resolving subcategory. So it's extension closed on the kernels of monomorphisms, kernels of epimorphisms, sorry, typo there, and contains all the projective modules. It also has enough injective objects, and the injective objects are obtained from the injective lambda modules by putting an injective, putting it on a vertex, and then inducing up to the full algebra. Okay. Yes. So sorry. So this are all the indecomposable injective objects in mono Q of lambda. So this explains the first of the two summands. Now for the non-injective part, you can look at monomorphic representations and look at them as representations in the stable category by just somehow taking a monomorphic representation and looking at it as a representation and then somehow factoring out, forgetting somehow injective summands if you want. And this is a functor, right? And this is in fact a representation equivalence. So it's full, dense, and reflects isomorphisms. But it's usually not an equivalence. In fact, it's an equivalence if lambda is hereditary, but usually not otherwise. Okay. So representation equivalents are very nice and important. One corollary is that it gives a bijection between the indecomposable objects in these two categories somehow. In the stable monomorphism category and the category of representations in the stable category. But unfortunately, we want to somehow take a representation in the stable category and construct back a representation in the monomorphism category. So that's somehow the wrong direction, right? We want to construct all the objects in the monomorphism category. So we would like to go the other way around. And this is possible, in fact. So this monomorphism category is actually functorially finite. So it admits minimal right approximations, which can be made explicit. And one can check that this construction, this minimal right approximation, is somehow well defined also on the stable category. So replacing this representations of Q in mod by representations of Q in the stable model category. And then you can obtain all the indecomposable non-injective objects in the monomorphism category as applying minimal right approximation, which is explicit, to all the indecomposable objects in this representations in the stable category. Okay, and that's all I wanted to say for today. Thanks.